This project is about consecutive sums, written and performed by Morgan Curley, Eileen Tucci, and Ina Aramandla. Let me tell you a story about a boy named Charlie.
Hi, I'm Charlie. I'm not voiced by a teenage girl. I'm just prepubescent.
One day, Charlie was walking through the park when he started thinking about consecutive sums.
Well,
he thought,
some numbers can be written as the sums of numbers that go in order when you count them. I guess these are consecutive sums. Hey, I think every number from 9 to 15 can be written this way.
Hey, Charlie, what are you thinking about?
I just made a discovery that the numbers 9 through 15 can be written as the sums of consecutive counting numbers.
You thought of all the numbers from 9 to 12 as sums of consecutive counting numbers, but 1 and 2 obviously can't be written that way. I wonder what other numbers could not be written as consecutive sums. Some numbers could be written as consecutive sums in more than one way. I wonder which ones. 9, 12, and 15 can all be written as sums of 3 consecutive numbers. I wonder if all multiples of 3 can be written this way. I wonder if you could write all multiples of 4 as the sums of 4 consecutive numbers, or all multiples of 5 using 5 consecutive
You two stupid humans! You seriously don't see it?
No.
Just be quiet and let me explain. Say you have a number and you want to figure out if it is a consecutive sum. Let's call this number n. Now, let's say you want to split n up into 5 consecutive addends with a starting addend of s. You would have s plus 1 plus s plus 2 plus s plus 3 plus s plus 4. Do you agree that this would be the sum of 5 consecutive counting numbers starting at s?
Yes, because there are 5 total addends, and as you add progressively higher numbers to the initial number, you should have 5 consecutive counting numbers.
Anyway, as I was saying, you would have n equal to the sum of 5 consecutive counting numbers. We could arrange this to be n plus s plus s plus s plus s plus s plus 1 plus 2 plus 3 plus 4, which is also equal to what?
Oh, it's n equals 5s plus 10.
Yes, that is correct. But we are going to keep the 1 plus 2 plus 3 plus 4 unsimplified. Do you know the equation for adding up the counting numbers to a specific number, including that number, kind of like a factorial, but with addition?
Oh, yeah, I learned that in math class. It's 1/2 times x plus 1.
Yes, because if you call the largest number in a set of counting numbers x, and add up the pairs of those numbers like Gauss did, then you will have a half x pairs of a value 1 greater than x, which, as Charlie says, is half x parentheses x plus 1, where x is the highest number, as well as the number of numbers in the sequence of consecutive numbers starting at 1.
Exactly. So in our case, because the sequence starts at 0, the highest term in the sequence must be 1 less than the total number of values in the sequence, and is represented by x minus 1, where x is the number of values in the sequence. Since these numbers are in pairs, and there are x number of values, the sum of the values in the sequence will be 1/2 x times x minus 1. Now, from our initial equation of 5s plus 1 plus 2 plus 3 plus 4, we can create a more general expression by replacing the number 5 with x and replacing the sum of the numbers that counted to 5 with 1/2 x minus 1, the expression for the sum of the numbers that counted up to 5. Now, if we set the equation equal to s, our starting value, instead of n, the consecutive sum, we can use our new equation to determine if different integer values are consecutive sums. Now we have the equation s equals n divided by x minus 1/2 x minus 1. Since we are talking about counting numbers, the equation will not hold if s is not a counting number, meaning that if s is not a counting number, then n cannot be a consecutive sum of x number of values. So in the end, the answer to all your questions can be found using the equation s equals n over x minus 1/2 x minus 1, which only holds if s is a counting number.
Wow! Whoa, I understand now. So I can take any value, then see if it can be split into a certain number of consecutive values using the equation. So, Allison, numbers that aren't consecutive sums are numbers that cannot be divided into a counting number by any number of addends.
Well, really, if that quotient can't be made into a counting number by subtracting half parentheses x minus 1, then n is not a consecutive sum. For example, 15 can be made into the sum of two consecutive addends because 15 divided by 2 minus a half parentheses 2 minus 1 equals 7.5 minus 0.5, which equals 7, which is a counting number.
On the other hand, 4 is not the sum of two consecutive counting numbers because 4 divided by 2 minus 1/2 times 2 minus 1 equals 2 minus 0.5, which equals 1.5, which is not a counting number.
Yes, and which numbers can be written as consecutive sums in more than one way?
Well, if the number is divisible by one odd number greater than 1 and not also divisible by 2 or divisible by 2 or more odd numbers greater than 1, it will be able to be written as a consecutive sum in more than one way. The odd number clause is true because if a number is divisible by x, an odd counting number greater than 1, in the second term of our equation, negative 1/2 parentheses x minus 1, when you subtract 1, you will produce a number that when multiplied by 1/2 will give you a counting number. Since both terms produce a counting number, the end result will also be a counting number.
Yes, for example, 9 is divisible by 3 and is not divisible by 2. It can be written as 4 plus 5 or 2 plus 3 plus 4.
Exactly! The reason some consecutive sums are not divisible by 2 is because the first and second term would both be fractions with the same denominators. The end result, or s, will be a whole number.
What about all multiples of 3 being written as the consecutive sum of 3 numbers?
Well, multiples of 3 are divisible by 3, and when 1 is subtracted from 3 to make 2, it's divisible by 2, and the resulting value will end up being a counting number.
Except for 3 itself, because 1 minus 1 is 0, and 0 is not a counting number.
Wait, in the initial scenario, back when we were using 5 instead of x, the equation for n was 5s plus 1 plus 2 plus 3 plus 4 equals n. And if we wanted to make that equation equal to s, like in our little master equation, we would have n minus 1 plus 2 plus 3 plus 4 all divided by 5 equals s. If we use 3 instead of 5, we would have n minus 1 plus 2 all over 3 equals s. Since 1 plus 2 equals 3 and n is already a multiple of 3, if you were to subtract 3, the result would still be divisible by 3. Unless, in the case where n is 3, because 3 minus 3 equals 0, and 0 is not divisible by 3. So the result is undefined rather than a counting number.
What about all multiples of 4 being written as the sum of 4 consecutive numbers?
Well, if we plugged in values consistent with a consecutive sum that is a multiple of 4 made up of 4 consecutive addends into the equation I was talking about, the equation would become s equals n minus 1 plus 2 plus 3 all over 4. Because 1 plus 2 plus 3 equals 6, and since 6 is not a multiple of 4, n minus 6 is no longer a multiple of 4. Therefore, the numerator cannot be divided by 4 to give a counting number. Thus, multiples of 4 cannot be written as 4 consecutive counting numbers.
But if multiples of 5 greater than 10 are consecutive sums of 5 addends, because with that reformatted equation you were talking about, n minus parentheses 1 plus 2 plus 3 plus 4 close parentheses divided by 5 equals n minus 10 divided by 5, if n is a multiple of 5 greater than 10, the value being divided will still be divisible by 5 to give a counting number.
Excellent. Now, bonus, why won't powers of 2 ever work?
Well, in our little master equation, s equals n over x minus 1/2 x minus 1, there are 2 terms. If x is odd, since powers of 2 can only be divisible by even numbers because the prime factorization is just a bunch of 2's, the first term would not be a counting number. However, the second term will not cancel out the fraction because an odd number minus 1 will be even and divisible by 2. So there will be a non-counting number minus a counting number, which is not equal to a counting number.
And if x is even?
Well, if x is even, then the first term would produce a counting number or a non-counting number that, written as an improper fraction, would not have a denominator of 2. However, the second term wouldn't be a counting number or cancel out the fraction in the first term because an even number minus 1 is an odd number, and an odd number divided by 2 can be written as an improper fraction that has a denominator of 2, and it is a non-counting number. Therefore, either the fractions from each term would not cancel each other out, or there would be a counting number minus a non-counting number. In either case, the result will be a non-counting number.
Exactly. Now maybe you will let me eat my bamboo in peace.
Hey, Charlie, I wonder if these same properties apply to factorials and multiplication.
Yeah! And maybe this formula can help form the basis of the Fibonacci sequence somehow.